Okay, so it's time to look at transportation energy. Overall, thus far, we know that our total lifestyle is about 600 gigajoules or about 600 bulbs on all the time. Our residential total is about 105 bulbs, for lighting, about 19 for heating water, about 14 for appliances, and about 66 for home heating energy. Now we move on to the next big wedge of the pie. In addition to residential energy, transportation energy. Now this is going to include both our passenger transportation in cars and light trucks and also commercial traffic. And that includes airlines and freight via trucks and trains, etc., etc. Now we want to try and gain some insight into why we use so much energy for transportation. It is a total of about 180, about that much, gigajoules per year per household of 2.5 people. So that's even more than the residential total. In fact, it's about 30% of our total energy use is for transportation. There's really three physical factors to consider. The first is the energy it takes to speed up the car. That gives the car kinetic energy. Remember that kinetic energy is a half times the mass times the velocity squared, where the velocity is in meters per second units. The next physical factor that we need to discuss is the drag force. Drag force is also known as the force of air resistance, and that's just the force that you need to move an object through the air, or in the case of a boat, to move it through the water. Okay? Now, the physical relationship depends on the density you're moving through, so there's more drag in the water because it's more dense, the cross-sectional area of the object, so a low-profile sports car has more drag, and then the speed of the object. Now it turns out that the drag force varies with the square of the speed. And the functional representation, and this is largely based on experiment, is a half times a constant known as the drag coefficient, more on that in a second, times the density of the medium that you're moving through, times the cross-sectional area, and then times the square of the speed. So the speed is really critical for the amount of drag force that we have. Now, this drag coefficient, it generally varies between 0 and 1, but it can be larger, and it reflects the three-dimensional shape of the object. Because if you look at these two objects, like a disk and a bullet, they have the same cross-sectional area, and if they're moving at the same speed, clearly the bullet's going to have a lot less drag because of its streamlined shape, although the cross-sectional area is the same. So we need a constant to reflect the fact that there's less drag on this shape than there is on this shape, and that is going to be reflected in this drag coefficient. So for something that's fairly flat, like this disk, the drag coefficient is quite large, and then for something streamlined, like the bullet or the airliner, the drag coefficient is quite small. The third physical effect that we need to discuss is the force of rolling resistance, and that reflects the fact that as you're driving down the road, your tire actually deforms and flattens out a little bit on the ground here. And the road actually is a little bit bent as well. And the result is that it actually takes energy to push the tire along the surface, because you've got to push this warped bottom around the tire, and there's steel cables in there that need to be bent. And you're also kind of always lifting it up over this little bump as you drive. You're kind of pushing the road. It's kind of like when you roll out dough, you're pushing that little bump in front of you down the road. Now, our model for rolling resistance is that the force of rolling resistance depends on a coefficient of rolling resistance, more on that in a second, and also the weight, mg, of the vehicle. Remember that g is the gravitational field strength, 9.8, m again is the mass in kilograms. What's the coefficient of rolling resistance tell you? Well, it's really dependent on the type of surface and also the type of wheel, so that if you have a really well-inflated car tire, it can be quite small. If the tire starts to get flat, the rolling resistance goes up. Okay, mountain bike tire, again, can be a little bit larger than a car tire because of all the knobs on it, but still relatively low. But then look at steel wheels on steel rails, extremely low coefficient of rolling resistance. That's just because the steel doesn't deform elastically under the weight as much as something like a rubber tire would. Of course, the ride is not as smooth, but then the energy expenditure is much smaller for rail travel. So let's do a calculation. Let's take a car, and we're given some data about the car, and see how much energy it would take to move the car a kilometer. So first of all, we'll start with the energy to speed up. Well, that's going to be the kinetic energy that we impart to the car. and that's going to be 1/2 mv squared. The mass of the car is given as 1,200 kilograms, and that's a fairly small car, right? That's like a four-door, a very small four-door vehicle. And we're told it speeds up to 14 meters per second. Okay, now dimensionally, a kilogram times a meter squared per second squared is a joule. And if we work out 1/2 times 1,200 times 14 squared, we get 117,600 joules, which is 117.6 kilojoules. All right, so that is one energy requirement we'll have to meet when we're driving, right? Because we're going to speed up from rest to 14 meters per second and then drive for a kilometer. Now, obviously, once we get up to speed, we're going to be working against a drag force. And we just wrote down the relationship, drag coefficient, air density, cross-sectional area, square of speed. So the car's engine is going to need to provide, via the wheels, enough force to move us forward. The drag coefficient is given as 0.3. Density of air, actually, that's not given in the problem, but it turns out to be 1.29 kilograms for every cubic meter, the density of air. Cross-sectional area of the car is given as 3.25 square meters, and then the speed of the car, 14 meters per second. Once we reach cruising speed, we have to square it. Now again, unit-wise, you end up with, although these are going to be force units, it's going to be kilograms times a meter per second squared, because the meter squared will cancel meters cubed, leaving 1 meter. One of the meters will cancel with that meter squared. So it's a kilogram meter per second squared, which you may remember from your previous physics courses is the definition of a Newton. And numerically, this works out to 123 newtons of force to move that car through the air at 14 meters per second. Now, that's the force. To find the energy requirement, we find the work, because we've got to provide 123.2 newtons of force. Remember, this thing here is a Newton. And then we're moving at 1 kilometer, which is 1,000 meters. Now, a Newton meter is a joule, so that's 123 2,000 joules. Newtons times meters is joules, or 123.2 kilojoules. So we got the energy to speed it up, and the energy to overcome drag being sort of the same order of magnitude. Next, we find the force of rolling resistance. That's the coefficient times the weight mg of the car. The coefficient of rolling resistance, we're just using the value from the previous chart for well-inflated tires. And then it's a 1,200 kilogram car, and there's 9.8 newtons for every kilogram. And that works out to about 352.8 unit-wise, kilogram cancels, newtons of force. That's the force to push the car down the road. And the energy will again be the work, so we're multiplying the force by the distance. 352.8 newtons of force. We're again moving at a distance of 1 kilometer. That's 1,000 meters. So that's 352,800 newton meters or joules, and that's 352.8 kilojoules. So we see that is a larger effect than either the drag or the speeding up and slowing down energy. The total output then, we're just going to add these three values together. That's the total energy requirement from our engine, and adding that up, the sum of those three, I get 470.5 kilojoules of energy requirement. Now, in terms of the energy output from the engine, the energy input, the gasoline energy, remember the efficiency ratio. Efficiency is an output over an input. The input to the engine is the gas energy. The output is the motion energy of the car. The required output energy is what we've calculated here. So in terms of the amount of gasoline energy we'll need to move this car 1 kilometer, it's going to be the output energy divided by the efficiency. So that's the 470.5 kilojoules divided by the given efficiency, which is about 15% for the internal combustion engine. And that gives us 3,000, 136 kilojoules, or 3.14 million joules, megajoules, to move that car 1 kilometer. Now, that figure, the number of joules to move the car a kilometer, is known as a cost of transportation. And in the textbook, we derived a value of about 3.7 megajoules to move a medium-sized car a kilometer. So that, certainly is well, or quite close to the value that we just calculated. Now, we used a value of 15% efficiency. That came from this graphic, which is from the U.S. Energy Agency. We see that although the engine is about 25% efficient, when you include the drivetrain losses due to friction and then idling losses, you only get about 14 to 16%, so about 15% efficiency overall. So let's use that value we just had of the 3.14 million joules per kilometer, so 3.4 megajoules per kilometer, and then use the average driving distance per year. Typical household in Canada drives about 24,700 kilometers per year. If we multiply those together, we get about 77,000 megajoules, so 77,500 megajoules per year, and then bumping that up one more metric prefix, we'll get 77.5 gigajoules per year. Now, just for comparison's sake, in the textbook, and earlier we referred to the fact that about 180 gigajoules was the total transport energy, but of course not all of that is for automobile transportation. About 47%, the value given in the book, was for the personal transport. The rest is for freight, and 47% of 180 is about 85 gigajoules. So again, our model, just for the one car that we took, we're getting a value that's pretty close to the average Canadian value. It's maybe a little larger just because not everybody drives Ford Focuses in Canada. There's larger vehicles, so the overall passenger vehicle total is a bit larger because of that. But certainly the right ballpark, and that's what we're looking for when we do physics, when we do modeling. We want to make sure it's in the right neighborhood.